sometimes first few weeks I got to keep track of which class I'm in that there. So, all right. I apologize for, like I said, for this week being a little bit hectic at their last week with EAC coming through. We've all been distracted trying to get our paperwork in order, and then of course between yesterday and today they've kind of cornered various faculty members to go over the course books and that kind of stuff. So we have not had the time to up there. But okay, in this particular case, since I'm just going through the slides, I did post these slides this morning on the e-learning site. So I'm going through the Bri slides. The other thing is, starting next week, we will be meeting on, see, this class meets Monday, or is it Tuesday and Thursday, right? Or no? You know, let me check my timetable here. All right, this class meets Tuesday and Wednesday. That's correct, right? We're 20203, correct? So starting next Tuesday, we will not be meeting in 314, but MPL 4 or MPL 2. It'll probably be MPL 4 next week, but then we'll be moving to MPL 2. That is a lab, so that we can start doing some labs in this class right there. So I said, starting next week, if I downloaded your newest timetable, you probably would see a room change, because I did the official. I did not change the lecture and lab. I don't, I asked her to do that. It didn't get but it doesn't matter. I'm going to be treating Tuesday as a lab time and Wednesday is our lecture time. So there's only one group for this class, so that makes it easy. I only need to worry about one lab time. Why they put us in this room for 314 for a lab when there's no equipment in that room or computers, I don't know. That was kind of a oversight of the scheduling person there. But we will get. I have moved this room. This time slot, there wasn't a lab available. That's why I flipped the two of them around out there. So hopefully, actually, we could go ahead and do an introductory lab next week, but it'll be on a different processor when I'm talking about. I think I'll wait another week before I do a lab. So next week will be a lecture. I'll just continue on the slides, and then I'm going to kind of deviate from the slides and go to the 8051, just to confuse people, just to confuse you. So, all right. Let me just kind of continue on right here where we were at. The last thing we talked about is, and I believe I started this subject, but I'm going to go ahead and continue on with it. That there is the microprocessor. It's called the CPU. It is the brains of any computer system. And I was supposed to bring in my motherboard today. That's what I forgot. That there, I knew there was something I forgot to do today. And this is the room that I bumped the projector. That there, I knew there was something I forgot to do. I was bringing my old motherboard. So between now and next Tuesday, someone's going to remind me to bring in the old motherboard. Okay, got there. And let me try. There is no Ethernet drop in this room here. I don't have an Ethernet cable. Well, even then, next Tuesday during the lab section, I think we won't do a lab, but we'll basically tear down the motherboard, pass the parts around, and kind of talk about each and every part of that. And that will be our lab section. We'll kind of tear down to look at a basic computer system right there. So, okay. The CPU, it's an IC. It's a single chip that you purchase right there. If you were to look at the first slide right there, if I was going to slide 1, but actually I'm not going to go to slide 1 here. I'm going to go to slide 1 here. It's one of these little chips. And why he does not show a picture of the 86 there, I don't know. But right there, it's just a chip on a motherboard. It's all it is right there. So, right there. And as I said, it's the brains of the operation. It really tells you pretty much how, when you look at the CPU of a desktop computer or a laptop, it kind of gives you an indication of the speed and the caliber of the machine you're dealing with that there. You know, so for example, Intel makes right now 3 microprocessors. One they're called the i3, the i5, and the i7. They're all very similar processors actually. That they're very much, when we look at the new generation of processors, they're very similar to the old ones. The biggest difference is that they have multiple cores. And we're not going to talk about multiple cores today, but I will mention that later on before we finish our discussion on the Intel processors. So again, a microprocessor contains just the CPU. There is nothing else involved in that there. It performs 3 major tasks. Think final exam question here, right there. I'll put a little star on that. Right there is what are the 3 major tasks of a microprocessor. It transfers data between itself and the memory or the I/O system. It controls all movement of data within the computer system, right there. That is all done through the microprocessor. There are some minor exceptions where, for example, some of the video cards will have their own memory and they'll do what they call direct memory access where they'll bypass the processor. Not very common. So for the most part, all data moves in and out from I/O through the processor, or from one part of memory to another part of memory through the processor, from one part of memory to the data card through the processor. It has to control everything out there. It does the simple arithmetic and logic functions. Now, that word simple is relative. When we look at the 8051, it has basically 3 to 4 arithmetic instructions: add, subtract, multiply, and divide. That's all that processor can do. The 8086, well, I should say the 8086, the 8083, the 8486, the Pentiums, the Core Duos, the i3s, i5s, they've got arithmetic functions such as sine, cosine, and exponent, and that kind of thing. So as we get into newer processors, the simple arithmetic operations become much more complex right there. Logic instruction operations, they can do and ors. They can do bit, shift left, shift right out there. But it does basic logic out there. And then it also controls the flow of the program via jump if not zero, jump if carry, jump. In other words, we can do things where we can jump around, we can do a branch, we can do a call, we can do an interrupt, all those things are controlled. So the processor controls everything. It controls all the flow of the data, it does all the math operations and all the logic operations, and it also controls the flow of the program. Again, you got to keep in mind what a microprocessor does is that we have a program right there, and it's a series of instructions. We'll look at how these instructions are, and it reads this instruction and it executes the instruction right there. And that instruction may be something simple like move into A, the number 35. That moves into a register called A, the number 35. It may be a call get ADC, and that's a subroutine call. But these are all instructions written in assembly language, and the processor controls the program flow right there. So it does that there. The program is your series of instructions, and the processor controls how each instruction is read and what the next instruction is going to be right there. The power of the processor is the ability to execute billions and millions of instructions per second. A microprocessor does very simple things, and when I say very simple, when you start looking at assembly language, you'll see that a processor, each instruction does very little. Very little. But its power is that it can do billions and billions and billions of these instructions in a single second, right there. Now, I shouldn't say billions, but millions, at least millions of well, into the billions. Yeah, we've got gigabyte processors that are into the billion, but you shouldn't say billions of billions. It's about a billion, 2.5 billion instructions a second or something like that. It's a lot of instructions per second right there. So, that is what makes it so powerful, is not what it can do in a single clock cycle, but how many instructions it can do, and the fact that we can store these programs in either the program memory of a microcontroller inside the chip, on our hard drive, in a desktop computer, in the BIOS of the desktop computer. But these programs can be stored and run over and over again. We can change the input to the programs to get different results out there. So these programs can do all kinds of things. And if you don't believe me, just look at your smartphone, and that you can see what type of things we can do. It can read a MP4 file and play a movie on your smartphone, with very, very high resolution right there. It can send text messages out through a cell phone service right there. It can access the internet through a data network. All this is done in something you fit in the size of your hand, and each instruction is really simple. So you cannot doubt the power of a microcomputer system today, right? There's just that there. I remember when I first started studying this, some people would say, why? Why are we doing this? This machine is so big and it does so little. And now we're looking at these machines are so tiny and they do so much right there. So, the world has changed in the last 35 years that I've been around computer systems greatly. Back in the early days, we looked at the 8085 and go, we could do this with other technologies quicker and faster and cheaper. And now we're looking at it and going, how did we exist without it right there? And your generation has never known what life was before computers. I can actually say that as an old man now. My dad used to tell me I didn't know what life was before television, because he grew up before the TV came out. So I grew up before computers, so I could joke with the young people about life before cell phones, life before the iPhone that there. So this is a relatively new technology, as we've been talking about that there. So that there, again, another power feature, it can make simple decisions based on, you can decide if a number is 0, positive, and so forth. That's all part of the logic flow that there. These instructions allow the microcomputer to modify the flow so the decisions appear to think through these decisions, simple decisions. There. You can write programs, and everybody's taken a course in C where you could do if, then, else, right? Well, those are the types of decisions. If A is greater than B, then do this. Otherwise, do that type of thing. So programs can make decisions based on the data and do various things. Your iPhone or your cell phone sits there and does nothing until you press an app. And then the software in the Android or iOS operating system tells it to open that application and run the application right there. So something in that software is telling it that it received an input and it has to do something based on that input. You key in an address in Waze, then that tells the software to download the map and start looking for that location. And then it tells the software to figure out what the best way to get there based on current traffic flow and all these various inputs right there. So, now let's get into the internal workings. A bus is a definition. A bus is a common group of wires that interconnect components. We have about 3 different buses we're going to talk about, and we'll go through them in a second there. Right there. They're used to transfer data, the address, and control information between the microprocessor, memory, and I/O. So right here are our 3 buses right there. We have an address bus, a data bus, and a control bus. Those are our 3 buses, and we'll see how those work. Some of those buses may be shared using the same wires. In particular, the data and the address buses are multiplexed, and we'll get into that here shortly. Right there. These 3 buses exist, and I just mentioned that there. That's just a repeat of what I just said right there. And figure here shows basically a block diagram of what a simple computer system would look like right there. We have the address bus right there. The micro P is the only one who can write to this. Only one that can write. Right there. So the microprocessor controls what address we're going to talk about, talk to memory. Now we've got our read-only memory, we've got our read-write memory, right there, often called RAM. We'll get into that discussion. In this particular case, we have a keyboard and a printer. Those are normally tied, again, through some I/O ports. That they're today's modern computers, almost all keyboards and printers are tied through a USB port. So this particular slide is older. That there, but what we're looking at there, I'm just going to use the word I/O right there for each of those. Just call them I/O. These are I/O ports right there, input/output ports, and these can be things like disk drives, right there. They can be printers, they can be keyboards, they can be mice, they can be anything you can think of attaching to your computer right there. Now, if you plug your camera in to a USB port, it's going to be treated as an I/O device. If you take out the memory card and stick it into a card reader, it's going to be treated as actually it's still an I/O because it's going to be going through a USB, so it'll be treated that there. Although the operating system treats Windows 10, I don't know about Windows or Mac OS. I own a Mac. I hardly ever use it. It's only used for watching movies from the U.S. is the only thing I use it for. That they're connected to my TV. It's a little Mac Mini. It's not really a Mac. It's a tiny, one of these little tiny Apple type things. But regardless, I don't know that much about Mac OS. I used to have a Mac, but I never used it with a card reader or a camera. I don't know how they mapped that there, but Windows 10, Windows 8, Windows 7 will map any type of card reader or camera or even an Android device you plug in and it looks like an external memory device is what it looks like right there. So if you plug in your Android phone to your desktop computer, you can copy files to it as if it's an external hard drive or an external thumb drive right there. At least that's the way mine works right there. But this is the basic there. These lines right there are not the names that they're going to be called in every processor. I mean, the author made these names up. These aren't even the names on the 8086, but we'll talk about what these four devices are. These control what's going to go on, whether I'm writing to memory or reading from memory, writing to I/O or reading from I/O. So we've got memory write, memory read, I/O write, I/O read. So we've got 4 lines right there, and the next few slides kind of talk about what those 4 lines do right there. So the address bus requests a memory location from memory or an I/O location from I/O devices. So the memory the address, the processor is going to place on the address bus a memory location. A memory location is like your telephone number or your address. It points to a particular place in memory, right there. And we'll look at memory in more detail, but memory, if you want to look at it, is this big, long series of boxes that each one of them contains a number. Now, it can be 8-bit numbers, so it can be 1011, 1100, but there, and each location has an address, FFFFF, all the way down to 00000. And notice that I'm writing these in hexadecimal numbers. I'm writing 5 digits because I'm using that a 20-bit address, which is what the 8086, 8088 uses. Other processors use different address, sizes. That there, the 8051 has a 16-bit address right there. The the i7 has a 64-bit address, if I'm not mistaken. I mean, so the address size varies from processor to processor. The size of these buses varies from processor to processor. I'll just leave it go at that. So not only does the address bus size changes, but the data bus size changes. So I'm talking right here about a 8-bit microprocessor that has a 20-bit address bus right there. So again, the address bus request is that there, and here, if the I/O address, the address bus contains a 16-bit I/O address between 000 hex to FFF hex. If memory is addressed, the bus contains a memory address. Again, this is what I was saying, varied in width by the type of processor. I showed a 20-bit address, which is what the 8086 has. The 8051 has a 16-bit address right there. So that there other processors have different addresses that there. 64-bit Pentiums that there. The Pentium has a 40-bit address that there allows up to 1 terabyte of memory that there. Now, the size of the memory or the address bus determines how much memory a processor can address. Right there. So one of the rules of thumb that there, and this is always going to be a test question. So again, if people are always, because there's a lot of questions on the first part of this course going into the theory behind the 8086, and they're easy questions to write. So problem 1 is going to probably have about 4 or 5 questions that's going to come out of this chapter. So this particular chapter has probably 15%, 20% of your final exam is going to come out of this particular set of slides and the next set of slides. And I know students want to know where the questions are going to come from, so I'm telling you that probably very few questions are going to come from any lectures before today. So today actually starts the material that's going to be on the final exam if you really want to know where things are going right there. So what we're saying is if the address bus is 16 bits right there, that means 16 bits line, you can address from 000 to 2 to the 16th minus 1 locations right there, or to the 16th locations right there. This counts as a location, so the top location is going to be F, 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 F right there. Now the simplest way of knowing what that is just to put in your programmer calculator, hit hex, and put F, 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 and that tells you that it will address 64K of data right there. If it's a 20-bit address, it will address 1 mega data. If it's a 24-bit address, it will address 16 mega data. Right there. Each time I hit an F, I add 4 more bits. So right now I'm at 16, 24, 28, 32, 36, 40. See, so 40 takes us up to our 1 petabyte that he was talking about right there. So, right there. So this is basically 1 petabyte is what that is, which some people might say that's more memory than you'll ever need, right? I had a senior faculty member back when I was a junior faculty member my first year of teaching scream and holler at me in a department meeting because I bought 4 IBM PCs and I bought them with 64K of RAM. And the reason he screamed and hollered at me and called me every name he could think of was because no one could ever write a program big enough to use 64K. Now granted, this was 30 plus years ago, but his attitude is that you could never write a program large enough to require 64K of RAM. It's physically impossible. It just can't be done. Yeah, and now I'm sitting there using a desktop with 64 gig of RAM, or 32 gig of RAM, not 64, but you can get up to 128 gig of RAM in a desktop computer, right there. So looking at this 1 petabyte and saying that that's more than anybody will ever use, we can't answer that question. That there's a law that was written back in 1968. It's called Moore's Law, and it's named after Gordon Moore, one of the founders of Intel. He said that every 3 to 5 years, the capacity of a microprocessor will double. I think he said every 3 years or something like that. And it is still true today. Every 3 years, processors get about twice as fast and twice as capable as what they were the previous 3 years. So as we look at that type of exponential growth in microprocessor power, 1 petabyte is not out of the realm of somebody needing that for some applications. Now, I don't see it in your smartphones, but on the other hand, I did not see people using 3 gigabytes of RAM in a smartphone 5 years ago. And I didn't see the need for a 128 gigabyte memory chip in a smartphone. But I've got one in mine. Of course, I carry about every CD that I've owned since I was 16 on my phone, right there. So if you were to look at my phone, you'd probably find, the person looked at it and said, memory chip's full, what he got on there. And when he looked at it and saw the music, then he realized that I must have been one of those long-haired hippies back in the 60s. That you saw the Black Sabbath and the Led Zeppelin and the Bob Dylan music, which most of you guys never heard of, but you probably heard of the Beatles, so I have some of that, right? You have heard of the Beatles. So, okay, but getting back to our discussion right here, when we're looking at our memory bus, one of the test questions will be if you have a 24-bit memory bus, how much memory can your system access right there? So we've got there. So the data transfer actually is what contains the information you're moving. So the address bus tells memory, I/O, and the processor. Well, actually, it doesn't know the processor because the processor tells the I/O and the memory where the data is. The data actually is what you're sending right there. Think of the address bus as containing your physical house address, and the data bus is the size package that's being delivered to your house right there. So the wider the data bus, the more data that can be transferred at one point at one time. Lanes of a highway. I was going into Los Angeles back in January, driving from San Diego on up through Los Angeles heading towards San Francisco, and I was on one highway that had 6 lanes going each way, a 12-lane highway. Not too many of those exist out there, but going through Los Angeles, and it was still traffic jam. Los Angeles is well known for traffic jams out there. So, but the largest data bus right now on a microcomputer is 64 bits right there. So that's a large. The 8088, which we're talking about, has an 8-bit data bus. Our 8051 microcontroller has an 8-bit data bus. Later on, I'm going to go through some slides. I'm going to go through why are we still using 8 bits when 64 bits are around, right there. But most desktop computers that we're using today are using either, if it's an older computer, it might be, I don't think any of these are around anymore. I think this is probably the standard today. And then you got to remember the i3 through i7, and there's been 6 generations of those processors. They follow the same, that their core dual or core 2 is actually 2 Pentiums on the same chip. That's what it is. That's why they call it a core 2. There's 2 Pentium processors. The i3 is a very large processor. The i3 I think has 2 cores. An i5 has 4 cores, and i7 has 8 cores. So, and when we talk about a multiple core processor, what that is you've got one chip here, and you've got 4 processors on the same chip that they're sharing the load. This processor might be doing the graphics, this might be doing some calculations, This might be talking to the hard drive. This might be doing something else. Or only one may be operating at a time. So we can have up to 8 cores on some of the modern processors. We won't be looking at multiple core processors in this class, but just to let you know, we're going to be lucky to get through and understand one 8-bit microprocessor very well by the end of the semester. Getting into these multiple core processors is beyond the scope of a one semester course, especially in electrical engineering, where you haven't had a lot of electronics there. So, because there's a lot of internal workings where these processors have to share information back and forth between each other. So going into these processors, these multiple cores, there's a lot of things that we're not going to discuss. But when we look at the Core 2, that was the first mainstream multiple core processor. So a multiple core processor, a lot of your cell phones, the Galaxy family in particular, I'm more familiar with the Samsung family than I am the Apple families. But the Samsung actually has 8 cores in their ARM processors, but only 4 cores operate at a time. So you're either in low speed mode, so your low speed cores are operating, and that saves power, but when you're playing a game or watching a video, the 4 high speed cores kick in and they operate and shut the 4 lower. So it only operates as a 4 core at a time. They don't operate all 8 cores simultaneously. You know, the ARM is only designed to be used as a quad core currently, right there. And the ARM again is just and the ARM is very complex because there's so many different versions of it, right there. So, but the data bus that there is 8 bits to 64 bits, right there. There might still be, I haven't seen them in a long time, but someone probably still sells them, some 4-bit processors out there. 4-bit processors were used way back in the early days, and they kind of stuck around for some really low-end applications. When I'm talking about low-end applications, I'm talking about this machine that raises and lowers the screen. It doesn't have to have a lot of intelligence there. But the cheap 8-bit microcontrollers, especially the ones that Microchip sells, the PICs, have pretty much did away with them, but there might still be some 4 bits out there. So microcontrollers that we'll talk about later typically only go up to 32 bits. Okay. Again, they talk about the average advantage of this, that it can send a lot of data at one time. Right there, there's a figure that they're all memories. Now, in Intel processors, even though you may have a 32-bit data bus, the data is still stored with 8-bit addresses right there. So if I look for a particular address and it's only 8 bits, I'm only going to grab those 8 bits out of that 32-bit data location. So it's still treated as 8 bits from an addressing point. If I'm trying to grab 32 bits of data, it's going to grab that bit of data, that 8 bits plus the other 24 bits that goes with it. In other words, it'll grab 32 bits, but I only give it one address, but it grabs 4 bytes at a time, right there. So, right there. So the Pentium, right there. And this is typically, when we look at the 8086, the 8088, this is a little hard to read. I put this here before. This is the one I'm going to talk about right here. See, it shows D0 through D7. That's 8 bits wide, and it goes from address 000 up to FFFF. That's what the memory looks like. When I look at right here, this is the 8086 and 286. This is 16 bits of data. What they're showing is that I've got a high bank and a low bank. These are my odd number locations. These are my even number locations right there. So if I'm going to grab 8 bits, I'll grab it from this bank right there. And again, as we get down to here, here's our 4 at a time. That's our 32-bit right there. And again, we're still looking at locations right here, but notice that and also notice that our address bus is getting bigger. So this is 1 gigabyte. This is what this one will address right there. So, and of course you can go on. This is the 64-bit map, and it's got 8 banks right there. And if you look at a memory chip, and doggone, I need to bring that board in. When I bring in my board, you look on the board, and you will see 8 chips on the board on these memory modules, and those are the 8 banks that they're talking about. So it's a little easier to see this when we see it on the memory chips right there. So, all right, the control bus I talked about before. There are 4 control buses that they're memory read control, memory write control, I/O read control, I/O write control. Only one of these can be low at the same time. And notice that there's the bar across, which means it's active low. So you can't do a memory read and a memory write in the same clock cycle, instruction cycle. You can only do one thing at a time. If you try to, and going back to my previous discussion, that only the micro P can write to these 4 lines. So the micro P controls the address bus and it controls the control bus. The data bus can be written to by anybody that the microprocessor gives it the permission to do that. And we're going to spend a fair amount of time looking at how that permission is given. In other words, we're going to look at address bus decoding and how we determine when we add a memory chip how the processor depicts that particular memory chip to talk to right there. So those are the 3 buses. So you need to know what those 3 buses are, what each one of them does, and the significance of the size of each of those buses. The control bus is actually the simplest one because it's got basically 4 lines no matter how big the processor line is. It doesn't make any difference how big the processor is right there. There are some other control lines in the control bus. These are the only 4 that are applicable to memory accessing and I/O accessing. Right there. So again, this is what typically happens right there. And let me go back to the previous slide here. I'm trying to get rid of this glitch. These are basically the 4 steps that happen in a what we call an instruction cycle. The instruction cycle first starts off with the processor puts out a memory address on the address bus. That's clock cycle number 1. Clock cycle number 2 is to send a memory read or a memory write signal out to that there. And this is going to be one of those 4 lines is going to go low. If it's talking to an I/O device, then it's going to take the one of the I/O lines low, and it can either read from an I/O device or write to an I/O device. So it's going to take either I/O write low or I/O read low. If it's talking to memory, it's going to take memory read write low or memory write low. Then the next clock cycle, the data is going to be latched into either memory or the I/O device, or put out onto the data bus by the memory or I/O lines right there. So it's going to but it's going to send the signal. At the same time it sends the signal, it's going to put the data out right there. But then it's going to that data is going to be latched into whatever device and then it's going to start the next instruction right there. And we'll look at some of these instructions. There may be some additional instructions. Very commonly, we will have an instruction in here where we do an address latch enable, where we will latch the address onto a latch external to the processor to save lines. Not all processors use a latching system. the 8688 does. So we'll talk about the latching system right there. All right, I'm going to skip through. Where am I at on time here? Okay, I know I'm in good. We got a good half an hour left to go, so I can go through all this right here very easily. So I got plenty of time right there. Okay, numbering systems. I'm not going to spend a lot of time on it. You just went through digital, most of you right there, and you had a final exam, so you should remember something about numbering systems, right? Right there. There's a couple of highlights in this chapter that were not covered in the digital right there, but the three numbering systems that you need to know: binary, decimal, and hexadecimal. Those were all covered in your basic digital right there. This section here, this is kind of a review right there. Numbering systems must be understood. First digit of any numbering system is always 0. Then decimal goes from 0 through 9. 8 goes from 0 to 7. Binary only has 2 digits, 0 to 1. Right there. And we did talk a little bit about octo, and I mentioned that there's a few people that did use octo. It's almost never used anymore. I haven't seen octo used in a microprocessor system. Obviously, the one that is most common is base 16. That there, and the reason base 16 is very common is that we group our numbers in groups of 4. You remember that I said that data buses are either 8 bits, 16 bits, 32 bits, or 64 bits. Those are all dividable by 4, so we can use 4-bit digits right there. Address buses are 16 bits, 20 bits, 40 up to 40 bits long, right there. All divisible by 4. So we can use hexadecimal as our main numbering system right there. So many years ago, octo numbers were popular. I will be honest, I would not have used the word popular. They were used. Only one company used them. It was a big company. It was PDP-11, the PDP-8. These were mini computers put out by Digital Equipment Corporation. They made the VAX, desktop or mini computer. So they all use octo. When I was a student, toward the end of my college days, my university bought a VAX, and we went to the VAX versus right there. And my very first email address I got, which is the same as my email address I use today, actually started was hack@cvax, which meant that it's cvax.ipfw.indiana.edu. That was my email address my very first email address I got when I was a graduate instructor at there. Next thing they did was my campus got their own internet connection, so the Indiana dropped off. And then they went to a common, and the CVAX dropped off. So my current email address is hack@ipfw.edu, and I still use that email address today. Right there. That's still a valid email address. It's not the one I use here. UniKL gave me one to use here, but this is my other email address. I also have another one that went through the same, which is ihack@purdue.edu. And it went through the same iteration. So I have 2 email addresses through my old university. One through the local campus and one through the mothership, we called it, Purdue West Lafayette. But this one also had a VAX number, AVAX, BVAX, whatever, .engineering, .purdue, right there. And all these various things went away, and now it's just hack@ipfw.edu or ihack@purdue.edu. This one I have to have the I in front because there's multiple hacks in the Purdue system, right there. So, right there. So when you look at email addresses, the point I'm making is the first that the VAX was a common computer used back in the 1980s, and they use octo right there. Digital Equipment Corporation went bankrupt somewhere right around 91, 92. No one else used Octo, so Octo's kind of disappeared. Right there. Right there. And again, this is, we're not going to, I went through, all this is digital. I'm not going to go through all this, the same basic discussion. Right there. Right there. And you've got copies of these slides so you can review them there. I will not have on the test conversions from one numbering system to another. That will not be on the final for this class, right there. I have enough to ask from that there. Now, that there, and this just kind of slides through here. Now, decimal is, decimal fractions, and that there. And again, I covered fractions, I think, briefly in digital, but we don't do it very often, so I'm not going to worry too much about that there. Binary coded hexadecimal, again, all that basically, that there is that it's, you're only using the digits there. The complements, we talked about 2 complements and 1 complement. Now, that there are some codes. I do point out that ASCII, Unicode, and BCD are not numbering systems, right there. Signed and unsigned integers, you do not need to know the difference between the two of those. But there, and what I did not talk about in digital, and I'll spend a few minutes talking about, are the floating point numbers, how those are represented, right there. So, right there. So those are the basic types of data that you're going to see in a microcomputer system. I'm going to talk today about floating point numbers. I'm not going to spend a lot of time talking about it. We're not going to use them. That there. That there. And the reason we're not going to use them is when we do computer programming, even for microcontrollers, if we want to use floating point numbers, 90.9% of the time we're going to use a compiler, and we'll let the compiler deal with how to handle the floating point numbers. We're not going to try to deal with floating point numbers in assembly language. That there. It's just too messy. That there. And doing the arithmetic and math is too messy. Right there. And in particular, the 8051, which is the processor we're going to be using for the lab, does not support floating numbers in its data structures. You can use floating point numbers, but the compiler has to handle it for you. And they have to put in multiples, and the compiler has to manipulate it. The i5, i3, and the equivalent AMD processors, they will handle the floating point numbers internally. They have a way of storing that there, and they can do floating point math internal to the processor. The early 8086, the 8087, or the 8086, the 8088 processor did not handle floating point math. So the processor we're talking about right now did not do floating point math at all. The floating point was added with the 8486, right there. If you wanted to do floating point math with the 8086 or the 8088, Intel sold a separate processor called the 8087, which was actually a math coprocessor. So the two of the processor and the coprocessor would act like multiple cores in a core duo. One processor would handle all the floating point math, and the other processor would do everything else. So the 8087 was a math coprocessor that handled all the floating point math, right there. So then there was an 8087. There wasn't an 8187 because the 186, the 188 were not around very long because Intel developed things in teams. This group of guys here, you're working on the 8086. You gals are working on the 8088. And as it turned out, the group that was doing the 286 was a much more competent group of engineers than those that were doing the 186. So by the time the 186 was ready to be released, the 286 was ready. Even though they started almost a year apart, the 286 team was just a better team of engineers. It just got their product to market much quicker, right there. So, and I suspect some people on the 186 might have gotten laid off at the time after that project was done. They sold a lot of 186s, but they didn't sell for desktop computers. Most of the 186s ended up in, of all things, HP printers. You know, they sold a lot of them, but they sold them to printer companies. They're the processors that ran the LaserJet printers right there. So, but we'll talk a little bit about the floating point. The other forms are available. ASCII codes, those are just, all it is a series of characters, alphanumeric characters. They're all represented with a 7 or 8-bit code. There's the 8-bit code, 7-bit code, and then there's the 8-bit extended ASCII code. You can look at that. There, you know, the number A is represented by, I think it's like 92. The big A is represented by 65 or something like that. So if I wanted to print a capital A, I would send 65 to my printer. If I was storing an ASCII text file, I would store 65 for that letter. Each letter or character that a printer could be printed had a number that represented that particular character out there. And even 0 through 9 was not represented by 0 through 9, but there was an ASCII code for each character that you could print. So you'll often see a single quote 0 like that. That means an ASCII 0. ASCII 0 is not equal to 0. I don't remember what it's equal to. I don't remember the ASCII code. You don't need to know the ASCII code that there, but it is a code that there. Unicode is a similar type code, but it was for a different family of printers. I think those were the IBM printers were a little different back in the 80s, so that they required a different series of codes. That their Unicode is kind of like octal. It's kind of gone away. It's not really common anymore. There. So PC and the extended ASCII is replaced. Character set is selected by placing a 1. That simply means the original ASCII set had 7 bits. 7 bits would represent basically 128 characters you could have in the standard ASCII set right there. When you use 8 bits, you extend the standard ASCII set, and now you have 256 characters in the ASCII set. And some of the characters are not things you would normally see, like backspace is a character, bell is a character, carriage feed is a character, line feed is a character, tab is a character. I mean, so if you send the ASCII code for a tab to the printer, it would put a tab in. If you put in the ASCII code for a bell, it would ring the bell on the printer. Most printers today don't have bells, but the older printers had bells. If you sent a carriage return, it would bring it back and give a single line feed. But you could do a carriage return with line feed or a carriage return with a line feed. There's all kinds of different things you can control your printer, but the ASCII code is that there. You normally do not do math with ASCII codes, but quite often you will process data. You'll send things to LCD displays, you'll send things to the computer display, and you'll send ASCII that there. But normally they're represented in most computer systems as strings or characters. So if you're looking at something you're defining as a char and you're using the single quote around it, what you're storing is the ASCII code for that particular character right there. If you leave these off, then you're storing the number out there. Some extended that there, again, there's all kinds of stuff in the extended that there. Extended characters can vary from one printer to another. That has kind of gone away. Most printers now use a common set right there. But there, and as I just mentioned, there are other control characters as part of the ASCII control set right there. Enter control key through the keyboard, so you can enter control 007, for example, I think is the bell or something like that. You don't use it very often, but you can do that. That they're stored. Now, some Windows applications use Unicode. Okay, I didn't realize. Now, Microsoft kept it around. This stores the 16-bit data, so that would probably be something like Word right there. Up there. Oh, okay, yeah, that's why they use the Unicode, is because that there is for Russian and Arabic and things like that is why they add that there. Okay. Again, I don't use Unicode, so I'm not an expert on Unicode. I've never used Unicode. I thought it went away with the IBM printers, but evidently, Microsoft grabbed it and used it for other things. Coded decimals is just simply the number 0 through 9 written in binary. Is all it is. It's a code that it has packed and unpacked forms right there. So 2 digits per byte right there, and it's used for BCD addition subtraction right there. So we don't use BCD very often, but BCD is used if you want to talk to the outside world. The reason you would use BCD is I've got an odometer in my car or a digital speedometer, for example, and if it told me my speed was F3, I would probably go, huh? Out there. I might go, huh? Yeah, but because I'll know what they're trying to say, but I don't know what F3 is. I can't convert that to decimal in my head very quickly to know what my speed is right there. So, F3, my speed is F3, what is that? F3 means my speed is 243 miles per hour, or kilometers per hour. I better not be going F3, right? That there. Regardless, if you saw F3 on your odometer, you would not, you don't want to drag out your hexadecimal to decimal calculator every time you want to check your odometer or your speedometer. So typically we would use binary coded decimal to show that there. Right there. Again, applications and point of sale terminals, if used complex, that their BCD is almost never used, and the reason is very simple, is there is no simple and effective way of doing BCD arithmetic. If you want to do BCD addition, subtraction, multiplication, and division, it's a pain in the royal tush. And I don't know if that translates to Malay very well, pain in the royal tush. But I think most people understand what I mean, right? Not easy to do. You don't want to do it if you can avoid it. Normally what you would do is you would do everything with regular binary or hexadecimal math, and then you would do a conversion to BCD just before you send it out to the output device. The same thing is if you're reading a keyboard or you're reading a keypad or something like that, you would convert it to regular hex or binary and do all your manipulations on it, and then you would then translate it back to BCD before you output it. You don't do very much with it internally in BCD. That's there. Byte size data. Now, we talked about this before, and I'm just kind of reviewing that they're in signed integer, it's the weight minus 128. But all they're saying is that when we look at, and this is kind of an easy way of looking at this, so do the 2's complement right there. If you look at this, it's got a value of negative 128 right there. All you do is you take this number right here and you add negative 128 to it, and that gets the equivalent 2's complement right there. So if I've got the number 1110110 that there, if I take this number now, I'm going to do this a little bit different here. I want to keep these right here because I want to come back to that there. Right there. If I want to take the number and 1101110, okay. Let's just go here and let's just clear this. Clear. And we're going to write 2 1s and a 0. 1 1 0, 3 1s and a 0. That's decimal 110, right? So if I take that decimal 110 and 110 minus 128, That means that that's the number negative 18. If I go back to my programmer, now the thing, if you're going to do this, you want to set in byte mode right there. You want to set in byte mode. And I put 18 plus minus, that's going to give me that same number back right there. So it's just a different way of doing it right there. Or you could just simply use the 2's complement and you end up with 18 right there. So that there. But again, this is the same as what we did in digital. So that there. Now, right there, negative numbers are stored 2's complement that there. Now keep in mind that when we're dealing with 16-bit, 18 or 16 bits, 32 bits, and 64-bit numbers, these ranges change greatly. Processor. This is for an 8-bit microprocessor, is what we're talking about here, right there. So if we're inside data, everything else is the same, right there. It's just at this particular point, what they're showing is that they're stored in 8-bit locations, but they're stored as a low order byte and a high order byte. So this represents the number 1, 2, 3, 4 hex is what that represents right there. So when we look at something that's defined as a word right there, if we define something at memory location 3000 as a double word, we can have right there, actually, this is what location right here. We'd have 5, 6, 7, 8, for example, going down that way right there. So, right there. So again, right there, we're storing that like that there. So again, he's showing here, we're going our high order byte down to our low order byte right there. He's just showing the same thing I just tried to show right there. And we're not going to worry about the big Indian format used with the Motorola family of processors, and it shouldn't be Motorola, it's now Freescale. Motorola sold off their microprocessor division to Freescale. So those of you that live in PJ probably remember a big plant out there called Motorola. That same building now says Freescale, right? Yeah, so they make processors there. So Motorola sold that off, but there's, it's still the 6800 family, 68,000 family out there. So, and again, we get into these are more numbering, real numbers. Now, real numbers is what we did not cover. And real numbers are, we have two parts to the number, and one is the mantissa, or the number itself, and the other is the exponent, right there. So now there are multiple ways of looking at it. Most computers store this as a fraction between -1 and +1. So it's actually negative 0.999999 to plus 0.999999 right there. So when we look at our format right there, 8-bit double precision, here's our sign bit. That tells us whether it's positive or negative. This tells us our exponent right here, the power in which we're going to raise this to, and this is our number itself right there. So if this is a 1 and this is a 4 and this is a 3, 5, 6, I'm just making numbers up here right there, that means that this is negative 0.356 times 10 to the 4th right there. Right there. Now, this also can be negative too, by the way. There could be a sign bit inside there too. In other words, this exponent can be times 10 to the negative 4 right there. So we have, but this is the way we store these numbers in that they're, as I said, I'm just introducing you to this format. Again, it's sign, exponent, and mantissa or significant. This is the number itself, and it's going to be point something right there. This is times 10 to whatever this number is right there, and this is going to tell whether it's plus or minus right there. So it's fairly straightforward that there. This really doesn't talk about using negative or positive exponents in this particular slide, but you can have positive or negative exponents that there. I have been working in this industry for many, many years. I've never had to deal with floating point numbers at this level. I deal with floating point numbers by using C, and I define a data type as a type, float, double, single, whatever, that there. I specify it as a floating type. I do floating point arithmetic in C, and the compiler does all this for me, and I don't worry about it so much. If I had some problems with the compiler and I've never had dealing with this, then I would be in trouble. I'd have to go back and review how floating point numbers are supposed to look like to make sure I'm getting the right results. That there. But again, this is using that there's single precision using a bias of 7F and double precision using a bias of 3F right there. So there. The assembler can define numbers that they're in single or double precision formats. That they're, again, remember the 8086 and the 8088, which is the processor I'm talking about for the beginning of this class, does not handle floating point. The 8051, which we're going to be talking about in more detail, which is a microcontroller, it does not handle floating point. In other words, you cannot use floating point types with those processors. You can only use integers. And if you want to use floating point math, you have to rely on software to, in order to generate the floating point and do the instructions. The software does a very good job. I mean, there's no reason why you can't use floating point with the 8051 or the 8086, except for your code gets very long and very drawn out. You normally would not use floating point, and this is a question I usually ask in the microcontroller course, but I'll just throw it out there. You would normally not use floating point with a microcontroller because the memory restrictions of a microcontroller are such that you want to save as much memory as possible. So you try to do your application where you don't have to use floating point. Obviously, if you're writing a payroll program, you would have to deal with cents, right? Pennies and things like that. If you're dealing with any type of engineering, you would deal with floating point numbers. You have to deal with floating point numbers. So they have to be part of the game that they're for desktop computers. For microcontroller applications, you try to avoid that because floating point adds a level of complexity to your code way beyond what you want to normally have on a small microcontroller. So optional directions are real 4, 8, and 10. Those are for the assembly language. Again, we're not going to deal with that. Okay, that wraps up this particular chapter right there in the book, right there. Remember, as I said, I see my time is just about right. So.